August 12, 1940, over the English Channel. The summer sun beats down on the cockpit of a Supermarine Spitfire as it climbs through a haze of sea salt and cordite. It is 11 a.m., and the air is thick with the roar of Rolls-Royce Merlin engines. For the pilot of this particular Spitfire, the world is about to tilt on its axis. He spots a Messerschmitt Bf 109 diving toward the white cliffs below and instinctively pushes his control column forward to follow. This is the moment where physics turns lethal. As the nose of the Spitfire drops into a steep dive, the pilot feels the light, lifting sensation of negative gravity. In that same heartbeat, his engine does something terrifying. It doesn't scream with power, it stutters, coughs a plume of black smoke, and suddenly dies. For several agonizing seconds, the most advanced fighter in the British arsenal becomes a multi-ton glider, leaving its pilot a sitting duck in the middle of the most critical air battle in human history. This was the fatal flaw of the early Merlin engines, a mechanical oversight that was costing the Royal Air Force its planes and its precious pilots. The issue lay deep within the engine's throat, specifically in the float chamber carburetor. This device was a masterpiece of traditional engineering, designed to mix fuel and air perfectly for combustion. It relied on a simple float, much like the one in a toilet cistern, to regulate the fuel level. In level flight or during a hard, banked turn that pulled positive gravity, the system worked flawlessly. However, the dogfights over the English Channel were chaotic. Three-dimensional dances that frequently involved pushing the nose down into a sudden dive. When a pilot performed this negative G maneuver, gravity ceased to pull the fuel toward the bottom of the carburetor. Instead, the fuel rose to the top of the chamber, forcing the float up and flooding the engine with an over-rich mixture that literally choked the fire out of the cylinders. This would be followed immediately by a total fuel starvation as the engine struggled to reset. The German pilots of the Luftwaffe were well aware of this British weakness. Their Messerschmitts were equipped with Bosch fuel injection systems, a technology that didn't care which way was up. When a German pilot saw a Spitfire on his tail, he didn't need to outturn it. He simply had to push the nose down and dive. The German engine would continue to hum with terrifying efficiency, while the pursuing Spitfire's engine would inevitably cut out, forcing the British pilot to roll the aircraft onto its back before diving just to keep the fuel flowing. This maneuver took time, and in a dogfight, a lost second was the difference between a kill and a funeral. By 2:30 p.m., on many of these frantic afternoons, the RAF would count the cost of these engine failures in burnt wreckage and empty hangars. The solution to this crisis didn't come from a high-ranking general or a massive industrial conglomerate. It came from a young woman named Beatrice Shilling, an aeronautical engineer working at the Royal Aircraft Establishment in Farnborough. Beatrice was not your typical wartime researcher. She was a woman who lived for mechanical precision and raw speed, often seen tearing around the Brooklands racetrack on her high-powered Norton motorcycle. She had earned a master's degree in mechanical engineering at a time when women were rarely allowed in the laboratory, let alone at the drafting table. By the time the clock struck 4 p.m. on a cold afternoon in late 1940, she had conceptualized a fix that was so brilliantly simple, it almost seemed like a prank. Schilling realized that the Air Ministry didn't have the time or the resources to redesign the entire Merlin engine or switch to fuel injection in the middle of a national emergency. They needed a stopgap. She designed a small brass diaphragm, essentially a metal washer, with a precisely calibrated hole in the center. It was officially designated the RAE Restrictor, but the pilots who would soon owe their lives to it had a different name for it. Miss Schilling's Orifice. This tiny disc was designed to be fitted directly into the fuel line of the carburetor. Its purpose was to restrict the maximum flow of fuel to exactly the amount the engine could consume at full power. This meant that when the aircraft entered a negative G dive and the fuel surged, the restrictor prevented the engine from being flooded. It was a crude, elegant, and incredibly effective hack that could be installed in the field by a mechanic with basic tools. Beatrice Shilling didn't just design the device, she took it to the front lines herself. Throughout the early months of 1941, she could be found riding her motorcycle from one fighter base to another, personally supervising the installation of her restrictor. Her presence on the airfields was a testament to the fact that the defense of Britain was a collective effort of intellect as much as it was of courage. By the time the spring offensive began at 10:15 a.m., on a bright April morning, the Spitfires and Hurricanes of the RAF were no longer choking when they chased the enemy into the abyss. They could dive, they could hunt, and they could fight on equal footing with the fuel-injected machines of the Luftwaffe. The legacy of Beatrice Schilling is not merely found in the blueprints of a brass washer, but in the survival of an air force that was on the brink of structural failure. Her genius lay in her ability to see a complex, life-threatening problem and solve it with a piece of metal no larger than a coin. She broke the barriers of her chair and the limitations of wartime manufacturing through pure, unadulterated competence. In the grand tapestry of World War II, we often focus on the massive movements of armies and the speeches of great leaders. But history is frequently steered by the quiet brilliance of those who look at a fatal flaw and refuse to look away. Beatrice Shilling ensured that when the pilots of the RAF took to the skies to def their home, their engines would be as relentless as their spirit, proving that sometimes the smallest components are the ones that hold the weight of the world. July 26, 1909, in the small town of Waterlooville, Hampshire, a child was born who would eventually defy every expectation of what a woman could achieve in a century defined by metal, fire, and the roar of the internal combustion engine. Beatrice Schilling did not enter the world with a silver spoon, but she certainly seemed to have a wrench in her hand from the moment she could crawl. In an era when young girls were encouraged to master the domestic arts, Beatrice was more interested in the way a gear tooth meshed with its counterpart. By the age of 14, while her peers were concerning themselves with the social graces of Edwardian tailored expectations, Beatrice was saving every penny of her pocket money to buy her first motorcycle. She did not just want to ride it through the rolling hills of the English countryside. She wanted to know why it breathed. She spent her evenings in a cold, dimly lit garage covered in grease and oil, stripping engines down to their barest components and rebuilding them until they hummed with a precision that surpassed their original factory settings. For Beatrice, this was never a mere hobby or a rebellious phase. It was a language. She spoke in gear ratios, fuel mixtures, and thermal dynamics. When the time came for her to pursue a career, she chose a path that was essentially a fortress of masculine tradition. She wasn't just choosing a job. She was declaring a quiet war on a status quo that believed a woman's place in science was as a footnote rather than a lead author. In the late 1920s, the gates of higher education were technically open to women, but the corridors within were often lined with skeptics and outright hostility. Undeterred, she enrolled at the Victoria University of Manchester, becoming one of only 2 women in the electrical engineering department. She was a lone silhouette of determination in a sea of charcoal suits and pipes. By 1932, she had earned her bachelor's degree, followed quickly by a master's in mechanical engineering. She didn't just pass her exams. She mastered the physics of motion with a clarity that often made her male counterparts look like hesitant amateurs. In 1936, Beatrice joined the Royal Aircraft Establishment at Farnborough, the prestigious nerve centre of British aviation research. This was a place where the future of flight was being forged in wind tunnels and high-pressure laboratories. Even here, in the supposed vanguard of technological progress, she was viewed as an anomaly. New recruits would often mistake her for a secretary until she began to speak, at which point her surgical understanding of aeronautics would leave them stunned. She specialized in carburetors and fuel systems, focusing her intellect on the very heart of the engine. Outside the laboratory, Beatrice lived at a speed that terrified most men. She was a legery motorcycle racer at Brooklands, the world's first purpose-built motor racing circuit. On her heavily modified turbocharged Norton, she became one of only 3 women to ever earn the Gold Star for lapping the track at over 100 miles per hour. This wasn't just thrill-seeking for her, it was essential field research. She understood what happened to an engine at the absolute limit of its urance, and she knew the smell of hot oil at 4 p.m. After a day of punishing trials, better than she knew the scent of any perfume. As the shadows of the late 1930s grew long over Europe, the Royal Air Force was desperately modernizing. The Spitfire and the Hurricane were the crown jewels of the British air defense, both powered by the legery Rolls-Royce Merlin engine. It was a masterpiece of engineering, but as the first dogfights began over the English Channel, a fatal flaw emerged. When an RAF pilot pushed the nose of his aircraft down into a steep dive to chase an enemy, the negative gravitational forces caused the carburetor to flood with fuel. The engine would cough, sputter, and momentarily cut out. In a dogfight, those few seconds of silence were the difference between a narrow escape and a fiery death. The German pilots, whose Messerschmitts used fuel injection, realized this and began using steep dives as a standard escape maneuver, knowing the British planes couldn't follow without their engines dying. While the senior engineers at Rolls-Royce were debating complex, expensive redesigns of the entire fuel system, a process that would have taken months they didn't have, Beatrice looked at the problem through the eyes of a racer. She understood that perfection is the enemy of the good when the enemy is at your door. Her solution was remarkably, almost insultingly simple. A small brass washer with a precisely calibrated hole in the center. It was designed to be fitted into the fuel line to restrict the flow of petrol just enough to prevent the flooding during negative G maneuvers. It didn't require a new engine or grounding the fleet. It could be installed in the field by a mechanic in a matter of minutes. Beatrice Shilling was more than just a technician. She was the bridge between the theoretical world of the laboratory and the visceral, life-and-death reality of the cockpit. She had spent her life proving she belonged in rooms where she was told she didn't fit, and in doing so, she created a device that allowed the RAF to fit through the narrowest window of survival during Britain's darkest hour. Her story serves as a profound reminder that the barriers we build around roles and gers are fragile things when compared to the force of a singular, focused mind. When we look back at the Battle of Britain, we see the contrails in the summer sky and hear the roar of the Merlins. We must also remember the woman who ensured those engines never went silent. Beatrice Schilling didn't just fix a carburetor. She engineered a future where brilliance is measured by its impact, not by the hand that holds the wrench. She remains a testament to the idea that true genius doesn't need a pedestal. It only needs a problem to solve and the courage to see it through. Her legacy is the quiet hum of every engine that refuses to quit when the world turns upside down. January 1941 at the Royal Aircraft Establishment in Farnborough was a time of frantic calculation for an engineer named Beatrice Shilling. The air was thick with the scent of high-octane fuel and the desperate pressure of a nation under siege. She understood that while the Battle of Britain had been won in the skies, the struggle for air superiority was moving into a more lethal phase. The Supermarine Spitfire and the Hawker Hurricane were the darlings of the public, yet they possessed a hidden, heart-stopping vulnerability that German pilots exploited with ruthless efficiency. When a British pilot pushed his stick forward to dive after an enemy, the Merlin engine would suddenly choke and die. For those few terrifying seconds of negative gravity, the fuel in the carburetor float chamber would rise, flooding the intake and starving the engine of air. It was a mechanical hiccup that translated into a death sentence at 20,000 feet. The German Messerschmitt Bf 109 did not have this problem because its Daimler-Benz engine utilized a sophisticated fuel injection system. This allowed Luftwaffe pilots to simply dip their noses and escape a pursuit. To follow them, A British pilot had to perform a clumsy, time-consuming half-roll to keep positive pressure on the fuel. In a dogfight where survival was measured in fractions of a second, this was an eternity. The problem was well known, but the proposed solutions were complex and required a total redesign of the engine's fuel system. This was a process that would take months or years that the Royal Air Force simply did not have while the bombs were falling on London. Beatrice Shilling approached the problem with the mind of a racer and the precision of a mathematician. By 10 a.m., she was hunched over blueprints, stripping away the unnecessary complexities her colleagues were obsessed with. She realized the engine didn't need a new heart. It simply needed to stop being overwhelmed by fuel. Her insight led to a solution that was elegantly simple. She designed a small brass disc, a washer with a center hole calibrated to limit fuel flow. This was the RAE Restrictor, though it soon earned a colorful nickname among ground crews. By 3:15 p.m. during testing, results were undeniable. The restrictor allowed fuel for maximum power but prevented the surge causing flooding during negative G maneuvers. It was minimalist engineering that didn't require a factory overhaul. It could be installed by a mechanic in minutes, effectively neutralizing the Luftwaffe's greatest tactical advantage. Schilling's work did not at the drawing board. She spent months traveling between airfields on her high-powered Norton motorcycle. She arrived at bases face smudged with oil to show ground crews how to fit the restrictor. Pilots and mechanics, initially skeptical, quickly respected her. They called the device Miss Schilling's Orifice, a name delivered with humor and gratitude. To them, she wasn't just an engineer. She was the woman who gave them back their ability to fight on equal terms. As the war progressed, the restrictor served as the vital bridge until a more permanent pressure carburetor could be fully integrated into the Merlin production lines in 1943. Yet, it is the simplicity of the restrictor that remains the most striking aspect of her genius. In an era of massive industrial production and increasingly complex weaponry, Schilling proved that the most elegant solution is often the one that changes the least to achieve the most. She understood that engineering is not about building the most complicated machine possible, but about understanding the soul of the machine well enough to fix its greatest flaws with the smallest of gestures. Her contribution was a turning point that went largely uncelebrated by the general public, yet its impact resonated through every successful sortie and every pilot who returned home safely. Beatrice Schilling's legacy is the ultimate victory of practical brilliance over institutional stagnation. She challenged the expectations of her genre and the limitations of her technology with equal ferocity. Today, we remember her not just for a piece of brass, but for the courage to look at a fatal defect and solve it with a steady hand and a clear mind. She is a reminder that in the grand machinery of history, it is often the smallest parts that hold the entire structure together. Her story is a testament to the idea that true genius doesn't need a pedestal. It only needs a problem to solve and the courage to see it through. Her spirit remains in the quiet hum of every engine that refuses to quit when the world turns upside down. A permanent tribute to the woman who ensured the defers of the sky would never be silenced by the very fuel that gave them flight. She stood as a beacon for future generations, proving that innovation is not always found in the laboratories of giants, but in the focused mind of someone who refuses to accept the status quo. The restrictor was more than a fix. It was a symbol of British resilience, a tiny ring of brass that kept the hope of a nation airborne. As we look back at the giants of the Second World War, we must look closely at that small device and remember the woman who looked at a flaw and saw a path to victory. Even in the darkest moments of human conflict, her story shows that one dedicated person can change the course of history through the simple, perfect application of truth and logic in every field of human endeavor. Her example serves as a guiding light for those who choose action over despair and simplicity over chaos. January 1941, at the Royal Aircraft Establishment in Farnborough, The air was thick with the scent of machine oil and the unspoken pressure of a nation fighting for its survival. The solution to the Merlin engine's most frustrating flaw was no longer a theoretical sketch on a drafting table, but a physical reality in the form of a small, precision-engineered brass restrictor. Beatrice Shilling did not wait for the slow, grinding gears of military procurement to approve a formal manufacturing contract. She understood better than anyone that time was the one resource the pilots of the Royal Air Force did not have. Under her direct supervision, the RAF workshops began a frantic pace of production, churning out the small metal discs that would soon be known across the front lines by their irreverent but affectionate nickname. By 6 a.m. on the first Monday of the rollout, Schilling was already at the airfield, her hands stained with the evidence of a morning spent in the guts of an engine. She was not a distant scientist watching from a laboratory. She was a hands-on engineer who preferred the roar of a hangar to the silence of an office. Schilling often traveled from one fighter station to the next on her high-powered Norton motorcycle, weaving through the English countryside with a crate of the new devices strapped to her bike. She would arrive at Biggin Hill or Kenley by 9 a.m. and immediately seek out the master mechanics, bypassing the officers' mess to speak the language of those who actually turned the wrenches. The beauty of the fix lay in its startling simplicity. To install the Orifice, a mechanic didn't need to pull the entire engine or perform a complex overhaul. It was a matter of unscrewing a fuel line, inserting the small brass diaphragm into the carburetor's fuel flow system, and tightening the connection back up. A skilled ground crew could modify a Spitfire in a matter of minutes. By 1 p.m. on those cold winter days, Schilling would often be seen standing on the wing of a fighter, showing a group of rapt mechanics exactly how to seat the restrictor so it would never vibrate loose during the violent G-forces of a dogfight. As the devices reached the squadrons, the tactical landscape of the air war shifted almost instantly. Before this mobilization, a Messerschmitt pilot could escape a Spitfire simply by pushing the nose down into a sharp dive, knowing the British engine would cough and die under negative gravity. But by 3:45 p.m., during a heated engagement over the English Channel just weeks after the rollout, the Luftwaffe found that the rules had changed. British pilots were now following their adversaries into vertical plunges, their Merlin engines roaring with a new, uninterrupted ferocity. The psychological impact was as significant as the technical one. For the first time, the RAF pilots felt they were flying a machine that was as aggressive as they were, a plane that would no longer betray them in the heat of a maneuver. The mobilization of Schilling's genius fix was a triumph of practical engineering over bureaucratic hesitation. It was a grassroots revolution carried out in drafty hangars and on the back of a motorcycle. By the time the sun set at 5 p.m. during those short winter days, dozens of aircraft were being cleared for combat with the new modification, each one a testament to a woman who refused to believe that a problem was unsolvable. She worked alongside the men, often late into the night, ensuring that every Hurricane and Spitfire in the southern sectors was equipped to fight on equal terms. Looking back at the giants of the Second World Air War, history often focuses on the generals and the politicians, but the true salvation of the RAF can be found in a tiny piece of brass that fit in the palm of a hand. Beatrice Schilling's legacy is not just found in the records of the RE, but in the lives of the pilots who returned home because their engines didn't fail them in their moment of greatest need. She represents the quiet, relentless brilliance of the British scientific spirit, proving that the smallest intervention, if applied with perfect logic, can turn the tide of a global conflict. Her story reminds us that progress is often made by those who are willing to get their hands dirty, and that a single calibrated whole can be more powerful than 1,000 pages of theory. In the grand machinery of history, it is often the smallest parts, designed by the most determined minds, that keep the entire world from falling apart. She looked at a flaw that threatened to lose a war and saw a path to victory, leaving behind a legacy of simplicity, truth, and the unwavering courage to fix what is broken. May 1941, over the churning waters of the English Channel, a flight of Supermarine Spitfires spotted a formation of Messerschmitt Bf 109s several thousand feet below them. In the months prior, a British pilot would have hesitated, knowing that a sudden nose-down pitch would cause his engine to sputter and stall under the force of negative gravity. But on this morning, the throttle remained wide open. The pilots pushed their control columns forward with a level of aggression previously reserved only for their German counterparts. As the Spitfires roared into a vertical dive, their Rolls-Royce Merlin engines did not miss a single beat. The fuel flowed steadily, the combustion remained constant, and for the first time in the air war over Europe, the mechanical disadvantage that had plagued the Royal Air Force was gone. This was the moment the technical playing field was finally leveled, not through a massive redesign of the aircraft, but through a small brass disc no larger than a coin. The Luftwaffe had long relied on the fuel injection systems of their Daimler-Benz engines to give them an escape route. When a German pilot saw a Spitfire on his tail, his standard maneuver was to dive hard. He knew the British carburetors would fail under the negative G-force, forcing the RAF pilot to perform a slow, rolling maneuver to keep the fuel flowing. By the time the British pilot recovered, the Messerschmitt was gone. But as Beatrice Schilling's Orifice began to reach every squadron across the British Isles, that escape hatch slammed shut. At 11 a.m., on airfields from Biggin Hill to Tangmere, ground crews worked feverishly to retrofit the devices. Schilling herself was often seen traveling from base to base on her Norton motorcycle, her hands stained with oil and her mind focused on the data. She did not just design the part, she ensured it worked in the brutal reality of combat. The pilots began to call it Miss Schilling's Orifice, a name spoken with a mixture of crude humor and immense respect. They knew that this woman, who outpaced most men on the racetrack, had given them the one thing they needed most: parity. The genius of the device lay in its sheer simplicity. While other engineers at the Royal Aircraft Establishment were debating complex pump designs and entirely new carburetor housings, Schilling recognized that the war would not wait for a perfect solution. She saw that the problem was not the carburetor itself, but the volume of fuel flooding the system during a dive. By introducing a restrictor with a precisely calibrated hole, she limited the fuel flow to the exact amount the engine could consume at full power. It was a stopgap measure, but it was a masterstroke of practical engineering. At 2:15 p.m., during a heated dogfight over the French coast, a young pilot found himself able to stick to the tail of a fleeing Messerschmitt through every twist and turn. For the first time, the hunter became the hunted in every dimension of the sky. This technical parity changed the entire complexion of the air war. The RAF no longer had to rely solely on defensive tactics. They could take the fight to the enemy with a renewed sense of confidence. The Merlin engine, now liberated from its fundamental flaw, became the legery powerhouse that would eventually drive the Allied air campaign all the way to Berlin. Schilling's genius was in her restraint. She understood that in the middle of a world war, time was the most precious resource of all. A perfect solution that arrived in 1944 would be useless if the war was lost in 1941. Her Orifice was the bridge that kept the RAF in the sky until more permanent pressure carburetors could be manufactured. As the sun set at 8 p.m. over the quieted hangars of southern England, the impact of her work was measured in the planes that returned home. Pilots who would have been lost to a stalled engine were instead taxiing back to their bays, their aircraft intact and their spirits high. Beatrice Shilling remained humble throughout the conflict, continuing her work at the Royal Aircraft Establishment, never seeking the limelight that her contribution deserved. She had looked at a complex, life-threatening problem and solved it with a piece of hardware that cost pennies to manufacture. This simplicity is the hallmark of true engineering brilliance. It reminds us that progress is not always found in the next great technological leap, but in the careful observation of why things fail. In the grand machinery of history, we often focus on the generals, the politicians, and the massive industrial shifts that define an era. But the story of the tiny brass orifice teaches us that victory is often found in the margins. It is found in the mind of an engineer who refuses to accept a flaw as an inevitability. Beatrice Schilling did not just fix an engine, she restored the balance of power in the skies. She proved that one determined individual, armed with a deep understanding of physics and a refusal to be intimidated by the status quo, can change the course of a global conflict. Her legacy is written in the vapor trails left by the Spitfires that finally flew without fear, a testament to the fact that sometimes the smallest parts are the ones that hold the world together. She left behind a world where the underdog had the tools to win, and her name remains a quiet anthem for every tinkerer and dreamer who knows that even the most daunting problems can be solved if you just look closely enough at the hole in the system. August 1941 at Farnborough. The air was thick with the scent of high-octane fuel and the relentless pressure of a nation fighting for its survival. Beatrice Shilling stood as a singular figure in this landscape, a woman who navigated the rigid hierarchies of British engineering with the same fearless precision she used to take corners on the Brooklands racetrack. While the world looked to the charismatic pilots and the towering figures of the high command, the real salvation of the Royal Air Force was being forged in the minute measurements of a small brass washer. It is easy to view history as a series of grand gestures and massive movements. Yet the story of Beatrice Schilling reminds us that the fate of civilizations can often rest upon a fraction of an inch. Before the arrival of Schilling's device, the Merlin engine was a masterpiece with a fatal flaw. When a pilot pushed his Spitfire into a steep dive to chase an enemy or evade a kill shot, gravity would momentarily betray him. The sudden negative G-force would flood the carburetor, causing the engine to cough and die at the exact moment life deeped on its roar. The German pilots of the Luftwaffe, flying their fuel-injected Messerschmitts, knew this weakness well and exploited it with lethal efficiency. They would dive, knowing the British could not follow without their engines cutting out. It was a mechanical Achilles heel that threatened to turn the bravest men into falling targets. The solution did not come from a massive redesign or a complex, costly project. It came from Schilling's realization that the problem was one of volume and flow. She designed a simple, small brass restrictor, a ring with a precisely calibrated hole that limited the amount of fuel entering the engine during those critical moments of negative gravity. It was so elegant and so effective that it could be installed in a matter of minutes by ground crews on the front lines. They called it Miss Schilling's Orifice, a name that carried the rough humor of the airfields, but also a profound respect for the woman who had given them back their wings. Think of the pilots who took off at 4 a.m. into the grey mists over the English Channel. Before Schilling, they carried a heavy weight of anxiety, knowing their own machines might fail them in the heat of a dogfight. After her fix, they flew with a new sense of freedom. They could dive, roll, and tumble through the sky without the terrifying silence of a stalled engine. This psychological shift was as important as the mechanical one. It allowed the RAF to reclaim the skies and to hold the line during the darkest hours of the 20th century. When a pilot engaged his target at 2 p.m. over the White Cliffs, he no longer had to fear the sudden cut of his engine. He had the full power of the Merlin at his command, thanks to a woman who saw what everyone else had missed. Beatrice Schilling's legacy is not found in grand monuments or heavily decorated medals, though she eventually received the OBE for her service. Instead, her legacy is found in the survival of a generation of young men who made it home because their engines didn't fail. It is found in the quiet corners of engineering history, where the unsung are finally being given their due. She was a woman who refused to be defined by the social expectations of her time. A woman who preferred the grease of a workshop to the comforts of a drawing room. She proved that brilliance does not care for gear or status. It only cares for the truth of the mechanical problem at hand. As we look back from our modern vantage point, we often forget how close the margin of victory truly was. We speak of the Battle of Britain as an inevitable triumph of spirit, but it was also a triumph of technical ingenuity. Schilling's brass ring is a metaphor for the power of the individual. In a world of massive industrial machines and global ideologies, one person with a clever idea and a steady hand saved the most iconic fighter plane in history. She did not just fix a carburetor. She repaired the broken heart of the British war effort. Her story asks us to reconsider what we value in our heroes. Do we look only at those who lead the charge, or do we look at those who make the charge possible? Beatrice Shilling was the silent partner in every aerial victory of the mid-war years. She was the shadow in the cockpit, the steady hand on the throttle, and the reason the Merlin engine became the leg it is today. Her work transitioned the Spitfire from a fragile beauty into a robust predator. Even when fuel injection eventually replaced the carburetor, the lesson she taught remained. That engineering is as much about understanding the spirit of the machine as it is about the physics of the metal. As the sun sets on the history of the piston-driven era, the name Beatrice Shilling resonates with a particular clarity. She represents the triumph of the tinkerer, the victory of the precise over the massive. Her simple brass ring remains a poignant reminder that even when the sky is falling and the world is at war, the solution might be sitting right there in front of us, waiting for someone with the courage to see it. It is a testament to the fact that greatness is not always loud. Sometimes it is as small as a ring, as quiet as a blueprint, and as enduring as the freedom it helped to preserve. She left behind a world where the underdog had the tools to win, and her name remains a quiet anthem for every dreamer who knows that no problem is too large if you have the vision to see the smallest part of the whole. She was the engineer who proved that while the great engines of war might roar, it is the smallest valves that dictate the rhythm of the heart. Her brass ring was a circle that encompassed the very survival of the free world, a tiny horizon that allowed the RAF to look toward the future without blinking. She was Beatrice Schilling, the woman who gave the Spitfire its soul and the British pilot his life.